Good morning.
Good morning.
Yeah, so before we get started, just wanted to make sure that you see that I voted this morning, and I want to encourage you all to do the same. All right, let's get started. All right, so we're going to work on heat capacity today. I want to remind you that there'll be no Zoom session next Monday. I'm going to be traveling that day, so I won't be having a Zoom session. I'm going to work around what we're going to cover that day, so we'll get everything done. Somebody needs to mute him, so not sure who. Thank you. Okay, so we're looking at heat capacity here, and heat capacity is based around a formula Q equals mc delta T, and it's more proof here that heat and temperature are not the same thing. They are related, as you can see here by this equation. Q is heat, m is mass, C is heat capacity of the object, and delta T is the change in temperature of the object. So what we're looking at, what is the final temperature of a 10.00 gram copper ring that absorbs 45.0 joules of heat? And here you would also need the heat capacity of the object. But let's talk a little bit about heat capacities. Well, one thing you've probably noticed is if you had a stove and you put a spoon on a stove, you know it heats up pretty quick. And that's because something like a spoon doesn't have very much of a heat capacity. And by heat capacity, what I mean is it's the amount of heat that can be absorbed by 1 gram of the substance to raise the temperature by 1 degree Celsius. So you'll see the unit here for heat capacity is joules per gram per degree Celsius. So the amount of heat required to raise 1 gram, 1 degree Celsius. So you know a spoon heats up pretty quick, but you put the same amount of water on a stove and it takes a lot longer. And that's because water has a much higher heat capacity. You know, the old saying, a watched pot never boils, because, you know, you're looking at the water, it doesn't seem to do very much. So let's look at how we can solve these kinds of problems. It says, what is the final temperature of a 10.00 gram copper ring at 20.0 degrees Celsius that absorbs 45.0 joules of heat? You know, the key word in this question is absorbs. And really, there's 2 words you'll be looking for in these kinds of problems. The word absorbs or the words releases. Now, absorbs means that it takes in energy. Anything that absorbs energy is going to go up in temperature. Anything that releases energy is going to go down in temperature. And I think that makes a lot of sense. So in this instance, we're looking for, we've got Q equals mc delta T. So we can rearrange this to find the change in temperature delta T. And the delta T here is 11.7 degrees. So the only question is, we know it's at 20.0 degrees initially. The only question then is, does the temperature go up or does the temperature go down? But since the word absorbs is here, we know that we would add that delta T to the initial temperature. And we know that then the final temperature is going to be 11.7 degrees more, which makes it 31.7 degrees. So in summary, what I can tell you is that if something's absorbing heat, the temperature is going to go up. If something is releasing heat, the temperature is going to go down. Does anybody have any questions so far?
So it looks like the heat capacity of the object kind of acts as the constant, right?
It is yeah, you'll always be given that value. You'll never have to memorize it or get it from, or you could get it from a table possibly, but it's not something you'd ever have to memorize, no.
Okay. And it differs from matter to matter, right?
Yeah, so from material to material, but it's constant for that specific material. So water is 4.18 joules per gram per degree Celsius, whereas copper is 0.385. So you can see that it's more than 10 times more. Water is 10 times more than copper is. And that makes a big difference to how these things act when they're heated. Now, the kind of problem you'll have to deal with in a test is something that relates to this kind of situation. So I've got a diagram down here that illustrates what's going on pretty nicely, I think. So it says a 15.0 gram iron block, and we don't know the initial temperature of the iron block, but it is put into 100.0 grams of water, and the water there is at 20.00 degrees. So you can see the picture here, and this is the initial situation. So we've got 100.0 grams of water. It's at 20.00 degrees. We've got a 15.00 gram iron block, but we don't know what the temperature is. Now, we know that the iron block is dropped into the water, and you can see that the temperature of the water has gone up to 22.00 degrees. And the question here is, what was the initial temperature of the block? Now, I think what's really important here is to really be cognizant of what you're looking for and what you expect to have had happen. Now, what I mean by that is that you can see that the water has gone up by 2 degrees Celsius. It stands to reason then that the temperature of the iron must have gone down. Because if you look at the diagram next to it, you can see that what's happened is that the iron has gone into the water must have absorbed heat. How do we know that? The temperature went up. So what other implication does that have? It means that the temperature of the iron must have gone down. Does anybody have any questions so far?
Are these measurements of heat exchange within a certain time period?
Well, it's until it reaches equilibrium, which I'm getting to in a second, Roland.
Oh, okay. Okay, gotcha.
So here's what we know. The iron block will release heat to the water, and the water will gain that exact amount of heat. That's the first thing we assume. The other thing is we get this final or equilibrium temperature. And that final temperature is going to imply that both the iron and the water are at that temperature. So what's happened here is that the water has gone up in temperature by 2 degrees Celsius. And we know that the iron has gone down, but it's gone down to the same temperature as the water, which is at 22 degrees Celsius. So Roland, to answer your question, what I can tell you is that it's done until the equilibrium temperature is reached, until we get that constant temperature. Now, at some point, obviously, the temperature is going to start going down, right, as heat gets lost to the surroundings. But we're making an assumption here. We're dealing with a system that is not really losing heat to the surroundings very much. Is that okay?
Yeah, that makes sense.
Okay. Does anybody have any questions so far? All right, so the main point I want to get across here is that the temperature of the water has gone up, which means we know that the temperature of the iron must have been higher than 22 degrees. That's all I really want you to get at right now. So when dealing with these problems, and I kind of made a big deal of this when we went through module 10, and I talked about word problems and how you can determine what you need to start with. And one of the keys is whatever you have the most information about is generally what you're going to start with. The other clue is what the question's asking for. In this case, it's asking for the initial temperature of the iron block, which means we can't be starting with the iron. We'd have to be starting with the water. Besides, we have a lot more information about the water than we do the iron. So where do we start here? Well, we start with this assumption that the iron block will release the heat to the water and the water will gain that exact amount of heat. So we need to calculate the amount of heat that the water is absorbing. That's the first thing. So the way we do that is we say, well, Q water, that's the heat that the water is absorbing, will be seawater, which is the heat capacity of the water. It's given in the problem here, 4.180 joules per gram per degree Celsius, times the mass, which we were also given, 100.0 grams, times the change in temperature, not the final temperature, but change in temperature, which is 2.00 degrees. Now, how did I get that? Well, looking at the problem, you can see that the water was initially at 20.00 degrees Celsius, but it gained a certain amount of heat, and now it's at 22.00 degrees Celsius. So delta T, the change in temperature, is going to be the difference between those two, which is 2.00 degrees, which I think makes a lot of sense, because what we're trying to do here is figure out, well, how much heat had to be absorbed by the water in order to raise that temperature by 2 degrees. Does anybody have any questions so far? So that comes out to be, sorry, Roland? Okay, that comes out to be 836 joules. Now that's the heat absorbed by the water. But as we discussed earlier, it also happens to be the exact amount of energy released by the iron, the Q of the iron. So what we can do, since we're after a temperature here, we rearrange this formula here to be delta T of the iron divided by, delta T of the iron is going to be the Q of the iron divided by the heat capacity of the iron and the mass of the iron. So the heat capacity of the iron here is going to be 836 joules, which is the same as the heat gained by the water. And then that's divided by the mass of the iron multiplied by its heat capacity, which comes out to be 124 degrees Celsius. But you've got to remember, this is a change in heat. This is a change in temperature, to delta T, change in temperature. Now, as we talked about earlier, the only discussion we have to have then is, was the initial temperature of the iron higher than 22 degrees, which is what it finished at, or was it lower? Since we know that the water went up in temperature, we know it absorbed heat. What that means is that the initial temperature must have been higher than 22.0 degrees. So it came out to be 124 degrees as being the difference. We add that to 22, we get 146. So that's what it was initially. So 146 down to 22, and that's where 124 comes from. Does anybody have any questions?
Where did the 0.449 come from?
That is the heat capacity of the iron, and you can see it's given in the question.
Okay, thank you.
So any heat capacities will always be given to you. You will not have to, you won't have to figure those out. Now, are you going to do a lab pretty soon? I'm not sure when. Are you doing a lab right now that involves heat capacities or not?
I think that's next week, yes.
That's next week, okay. Yeah, so you'll actually be doing a lab where you calculate the heat capacity of a metal. And what you'll actually be doing is measuring the temperature difference in a similar fashion to what we're doing here in this problem. You'll be taking a metal and then putting it into water at a known temperature and seeing how much the water goes up by. And that allows you to be able to calculate the heat capacity of the metal. Not exactly the same problem as we're doing here, but pretty similar. So that'll give you a real practical basis for seeing what we're looking at here in this kind of problem.
Yeah, it's this week. Sorry, I had to double check.
Okay, no, that's good. Well, it's nice then, isn't it?
Yeah,
It's almost like it was set up that way. All right, does anybody have any questions?
So in this question, we're trying to get seawater.
No, in this instance, we're looking for, if you look at the question, it says, what was the initial temperature of the iron block? That's what we're looking for, David.
And you do that just by doing 4.18 joules. I don't get it. Can you show me the equation again?
Sure. Because we're looking for the temperature of the ion, it means we have to figure out how much heat was absorbed by the water first. And that's down here, David. Q water is equal to C water times M water times delta T water. The delta T being 2.00 degrees, the difference in temperature. This is how much heat, 836 joules, was absorbed by the water, which happens to be the amount of heat released by the ion. Does that make sense?
Yeah, and then you convert it to C. You look at the initial temperature of the iron, you add it. It makes sense.
Okay. Well, you know, the main thing then is to figure out the change in temperature of the ion using the formula here, and assuming that the heat released by the ion was the same absorbed by the water. And that's really the key to this. Is that okay?
Okay. Yeah, that's fine. That makes sense.
Now, there's actually two kinds of problems that you could possibly see on the test. What I'm going to do is show you, I'll show you the practice quiz here, which has very similar problems to what you're going to see on the test as well. So that's one kind of problem where we're looking for the initial temperature of the ion. We can also reverse the problem as well. And we can look for the initial temperature of the water. It's under heat capacity. Here we go.
I did have a quick question about
Yes, Roland.
capacity. Well, heat capacity trends. So like I was kind of looking at the equation. So like I guess if the higher the heat capacity is of the object, the more energy it takes to heat that thing up, right?
Yes, if you're comparing equal masses of things, yes.
Okay, so like I would say that insulation has a higher heat capacity than say a piece of aluminum or something.
Absolutely, yes, and that matters, right? Because you don't want your insulation to heat up, do you?
Exactly, you want to keep the heat out, so you don't want it to absorb all that energy.
That's right. That's why it takes so long for a pot of water to boil versus to heat an empty saucepan.
Yeah, and then it's the same thing with like why humidity, like if your house is humid, it'll stay cold or hot because it takes more energy to heat the water in the air, right?
Right, that kind of thing. Mm-hmm.
Okay.
Yeah, but water is a real bear when it comes to heat capacity. It's such a high heat capacity. But that's part of the whole global warming thing as well. And the oceans have a huge capacity to absorb a whole lot of heat, which is why these changes are so slow. And there's so much water, and it has such a high heat capacity that we're seeing changes, but we're seeing them on a very slow scale because of that.
And then it takes a long time for them to lose the energy too, because it doesn't want to give up energy. Okay.
No, that's right. That's why we get hurricanes in October and November, because it takes so long for the water that's been heated up during the summer to cool down. So it's kind of displaced a bit, the timing. All right, let's take a look. The second question here, I'm looking at question 2. And this is the opposite kind of question to the one we just looked at. Here in this instance, we're given a 200.0 gram tin rod. It's heated to 178.0 degrees Celsius. It's put into 100.0 grams of water. We know that the equilibrium temperature is 30.5 degrees Celsius. So the equilibrium temperature is the final temperature of both the water and the tin rod in this case. What we're looking for here is the initial temperature of the water. So I'm going to go ahead and do this problem here and show you it's a little different to what we just did. A little different, but we do use a similar strategy here to solve this kind of problem. So looking at this, we know we're looking for the initial temperature of the water. That's what the question's asking for. So I know I can't be starting with the water. I have to be starting with the tin. So my first stop here is to say Q Sn, which is tin, is going to equal M Sn C Sn delta T Sn, where Sn is tin in this instance. Okay. Now the mass of the tin, we're told, is 200.0 degrees. Sorry, 200.0 grams, sorry. The heat capacity, we're told that down here, 0.210, it's in the problem. Joules per gram per degree Celsius. You'll notice that I use units here. I can't count on you to use them, but I think it's useful to do the units every time you do these problems. The delta T is going to be 178 minus 30.5. Now, trying to keep significant figures here, which is going to be based upon number of places past the decimal, it's going to be 147.5. So that tells us the amount of heat that must have been, well, you got to say, well, was it released or absorbed? So what did the tin do? Did it release heat or absorb heat? Does anybody know? It's an interesting question. Anybody know what happened? Did it release or absorb heat? It's not a trick question.
It looks like it releases heat.
It does. How do you know that, David?
Just reading it, it says it's heated to 178 degrees C. It's placed into water, and then it goes down to 30 degrees C.
Yeah, so in order to go down, it must have released heat, right?
Of course.
Yeah, that's good. So 6195 joules. Now, in order to keep up with the sig figs, it really should be 6200, but I'm going to just keep the sig figs the way they are because we're looking for something at the end here, not around at the end. So we're looking for, we got Q water next, and that equals mass of water times C of water times delta T of water. Now we want the initial temperature of the water, so we're interested in delta T. So delta TW is equal to QW over CW times MW. Now the Q of the water is going to be the same as what it was for the iron, so 6195 joules. Now the Q of the water, that's the amount of heat that was absorbed by the water. Okay, that's important, right? The heat was absorbed by the water. We know it was absorbed because the iron released heat to the water. So it must have absorbed that. 4.18 joules per gram per degree Celsius.
Can you see?
No, we can't.
And then the mass of the water is 100.00 grams. Sorry, 100.0 grams. So I do the math on that. This will give me the change in temperature of the water. You'll notice it will be a lot less than the iron because the heat capacity is higher. All right, I get 14.8 degrees Celsius. Taking that down to 3 sig figs. So what's this represent? Well, this represents the change in the temperature of the water. So the question has to be for you, well, what was the water before? Was it higher than 30.5 degrees or was it lower than 30.5 degrees? And the answer to that question has to be lower than 30.5 because we know that the iron released heat into the water and brought it up to 30.5 degrees Celsius. So the initial temperature of the water, you see the difference here is going to be 30.5 degrees Celsius minus 14.8 degrees Celsius. So that comes out to be 15.7. Which I think makes sense because you say, okay, so the water was at 15.7 degrees Celsius initially. Then we put the iron in, sorry, tin. It went up to 30.5 degrees because the tin released a whole bunch of heat into the water. So it absorbed heat in order to become 30.5 degrees Celsius. Does anybody have any questions about this kind of problem? So hopefully you can see the difference between this one and the one we just did. You could get either one of these problems on the test. You just have to be prepared to be able to do both of them. Does anybody have any questions? Yeah.
Will these formulas be given, or is this something that we're supposed to remember because we?
I think it's Roland, I think it's given.
Okay.
The heat capacity is definitely a given, but I believe that I put the formulas here in the actual test, so you won't have to memorize them. But I mean, it's just Q equals MC delta T. You'll have to know Q of what, obviously. In order
I know what you're looking at too, for sure. Yeah.
That's right. But yeah, we'll take a look at that when we get to the test, and we'll see if I'm lying or not. But I don't think I am.
Too easy.
What's that?
Oh, too easy.
Yeah, that's right. All right. Does anybody have any questions?
Yeah.
Yeah.
Why did you need to get 6,195 joules at the start? Why did you need to get QSN? What do you use that for?
Well, what I'm trying to figure out is how much heat the water absorbed, because that's going to be the same as the amount of heat that the tin released into the water. You see, the thing is that energy can neither be created nor destroyed, David. So if something's releasing heat, something must be gaining it. So if the tin is releasing heat, it must be the water that's picking it up. And what I want you to see there is that because the water is absorbing heat, it must be going up in temperature. That's the main point that I'm trying to get across here.
Okay. So for QSN, you're figuring out how much the tin releases heat, you said?
That's right. And that equals the amount of heat absorbed by the water.
All right. Okay.
Yeah, it's just one of the assumptions that we make because we know that the heat's got to go somewhere. Right?
And we can say that heat is energy because heat is just the measurement one of the measurements we use for energy, right?
That's right.
Okay.
Joule, but it's in joules. Anything with joules is going to be energy.
Okay.
Whether it be heat or whatever else. Okay. Any other questions? Okay. So you can expect one of those kinds of questions on the test. Let's take a look at the test. And we'll see how that works. Take it back here. Let's see. So we're looking at question. Just got to find it here. Where is it? It must be further down here. Here we go, heat capacities. So it's question 13 and 14. It looks like actually you get one of each kind of problem. Possibly. No? Looks like you get two problems and they could be either, I suppose. All right. Looks like these two are two of the same kind of thing. But you could get either kind of question for that. Let me look at the top here and see what you've been given. I'm just looking to see if you've been given that formula or not. It looks like I might have lied. So I'll make sure I add that formula in to the questions, okay? Or at least at the top of the questions. And I'll make sure it goes in here somewhere. Sorry about that. I do need to include it though. I had meant to. All right. I'll fix that up. Let's continue on with what we're doing here. The other application we have for delta H or heat of reaction is that we can use it in stoichiometric type situations as well, which allows us to determine the mass of something that releases a certain amount of energy, or starting with the mass, we can figure out how much energy something releases. And the key to this is the delta H value, which you'll notice is not in kilojoules per mole, but kilojoules, because it's specific to that specific reaction with this specific stoichiometry, meaning 2 moles of methanol, 3 moles of O2, 2 moles of CO2, 4 moles of H2O. So it's not per mole of any one thing, but it is the delta H for that specific reaction. For this one, we can see that the delta H is negative, which indicates that it's releasing energy. And that's fine. That's really not necessary information, but it's good to be able to look at that and be able to make that determination. One thing, I'm going to mention this now. One thing I'm thinking of starting this, requiring people to have their video on during these Zoom sessions. And I'm not going to require it today, but what I'm going to ask for is, so since you're here, I'm going to ask for feedback as to why I shouldn't require that. I mean, I can tell you the number of times that, you know, I've ended a session and there's been a whole bunch of people left at the end. I know that they're not at their computer, so I just don't see what the point is. So, you know, I'd like to know that people are paying some modicum of attention to me. It's kind of a bit lonely up here just talking and just wondering if people are actually even listening to me, or if I'm just talking to myself. I don't know. I've got no clue. Nobody has their video on, so I have no idea. So I'm thinking about doing that. I know I didn't require it in the syllabus, but I'm thinking of doing it from this point forward. I mean, from the next lecture forward. So if anybody has any true objections, I want you to give me some feedback and tell me why you don't think it's a good idea for me to require that you have your video on. All right.
I understand where you're coming from, but I feel a lot more comfortable taking notes this way and getting relaxed and having all my papers spread out, but I understand where you're coming from.
Yeah. But anyway, you know, I get it too. I mean, from other people's point of view, I mean, there are some people out there though who just want to have their name up here and they don't want to listen. They want to multitask. They want to do something else. But I'm trying to have that balance, you know, and I would say that if people don't want to be here, don't want to listen, then just watch the recording later. Don't even turn up. That would be my thought. Because if you're not going to get anything from it, then I don't see the point.
I understand.
I personally think that it would be different if you didn't require it and I had my video on, then I'd be uncomfortable. But for me, it's like if everyone has to have their video on, then I don't really care. So if like you make it required and everyone has to do it, it's like, yeah, sure, why not?
Right.
And I guess for me, I personally do not care. However, I know that like I understand your concern about like, oh, people are not showing up or they're not really they're half paying attention and stuff like that. And I would just say it's their loss because they're not getting the information that they need. So it's sort of like double work, you know what I mean? Because you might as well pay attention here instead of like going back and doing it over again. So I don't know. It's sort of a double-edged sword.
Yeah, I don't know. It's something I've struggled with, you know. It's something I've struggled with. Yeah, so I'm sensitive to people's desire not to be looked at, which I get, I suppose. But at the same time, if you're in a classroom, you know, it's unavoidable. You know, in a classroom, for example, I don't require that people not text. And you know, if somebody wants to text the entire class, well, you know, I might not like it, but I deal with it. The difference here is that I don't know what people are doing. Therefore, I can't judge. And you know, I think that's part of it too. But anyway, have a think about it, folks. If anybody wants to object seriously, or I mean really object, I mean send me an email, and you know, I'll take anything into consideration here. All right, let's continue on with the stoichiometric enthalpy. So you've been given a problem. What mass, and we're looking for a mass of methanol here, must be burned in excess O2 to liberate that much of energy. Now the excess O2, that's kind of important because what it means is that we know that the methanol is a limiting reagent. So what that means is that we've got enough oxygen there to burn all of the methanol that we have. It's not like we're depriving the situation of oxygen so that we can't burn every bit of methanol. So that's what the excess is indicating. It's not really germane to the problem though, as it turns out. The only figure we actually have here to start with is the energy. So that's what we're going to start with, 8.00 times 10 to the 6th joules of energy. So I'll just write E6 joules. And we are given an energy here in kilojoules here. So we know that we're going to have to do a conversion. So it's going to be times 1 kilojoule over 1,000 joules. The centerpiece of the problem is the stoichiometry, because we know that 2 moles of methanol are required to produce the amount of energy that's given at the end here of the reaction. Remember, you are given this reaction. This is not something you have to figure out. So it would be, well, to make it cancel, we know kilojoules have to be on the bottom, and we know moles have to be on top here, and that'll eventually give us grams. So it's 2 moles and 790.3 kilojoules. And then it's times the mass, the molecular weight, which would be 32.05 grams CH3OH over 1 mole of CH3OH, because that's the molar mass. And that gives us the mass of methanol, 649 grams. Now, a common question people are going to have here is, well, what happened to the negative? Why did I take the negative out here? Because there's negative here in the problem. Why did I put the negative here? Well, the question, it's a semantic one, because I look at the wording and said, what mass must be burned? What mass must be burned? Now, if I leave the negative in there, it comes out to be minus 649 grams if I left it in there, which would indicate that that's how much methanol was lost. But it's kind of asking for how much was lost, and that's going to be a positive value, not a negative value. So the bottom line here is if you see a negative, I generally will just ignore it because I want to answer the question, what mass must be burned? So that's going to be a positive value. Does anybody have any questions?
So you said you ignore the negative value because it's looking for a positive value.
That's
disregard.
Yeah, that's pretty much right, David. Yeah.
All right.
Now, would it be completely wrong? No, I don't think so. I mean, if you left it as negative, I kind of understand, but it meant that that's how much was lost. But it's not really answering the question. Not really obeying the wording.
Okay.
So you don't have to do anything special at all. It's just as simple as taking the negative out of your answer.
That's right. It's just so we get the we get the answer we're looking for per what the problem is asking for.
Okay.
So in this instance, the other thing we can do is we've got 50.0 grams. We can figure out how much energy that releases. And it's kind of the reverse. But you'll notice that I use dimensional analysis in order to achieve this. So 1 mole of CH3OH and the molecular weight here is 32.05 grams. So that's how much 1 mole weighs. And the reason I'm doing this is because I want to get these grams to cancel. I've got moles here. And I know in the next step, the moles have to be on the bottom now. So moles of CH3OH have to be on the bottom. And then I've got my energy, which is in kilojoules. And that's 790.3. So again, for the same reason, I make it a positive value. And I put 2 moles here. Now the 2, of course, comes from the stoichiometry, from the reaction. And then we're looking for joules, so we do a conversion at the end, joules to kilojoules. 1,000 joules and 1 kilojoule. And that gives us, in this case, 6.16 times 10 to the 5th joules. All right, does anybody have any questions? So you'll get one of those on the test as well. It's not a particularly difficult problem, as long as you're aware of the centerpiece of each kind of example, this business here, which comes from the reaction.
I have a question.
Mm-hmm.
So for the first question, how do you know that it needs to be 2 moles of CH? Was it CH3OH?
Yes, it's from the reaction. Remember, you are given this reaction, David.
That reaction gives us that amount of energy, like always.
Yeah.
Is that what it is?
Well, yes, but specifically 2 moles of methanol, CH3OH, are required to produce this amount of energy. Just
Okay.
like 3 moles of O2 or 2 moles. See, I could ask for anything here. I could ask for O2, I could ask for CO2. You would just pick out the number in front, because that's how many moles are required to produce this amount of energy.
All right. And then you multiply it by the molecular weight.
Yeah, it's because if we're starting with joules in the first one here, we know we're getting to kilojoules because we've got kilojoules in the problem here. But then we also need the moles, which will give us the grams.
All right. Yeah, that makes sense.
Okay.
It's just like a long conversion.
It is. That's the way I want you to treat it, but just step by step.
Got it.
All right. Does anybody have any questions? Okay.
Pretty straightforward.
So we're going to move on now. We'll talk about energy and light here. I know I was going to cover this on Wednesday, but we're going to work a little bit ahead here so that we can get a little bit ahead for when I won't be here next Monday. All right, let's first of all talk a little bit about the electromagnetic spectrum. And I'll do a search. And I'm just going to come up with a all right, so this is a very rough, gives you a rough idea of what you can see here. I would have liked some kind of wave. I don't like this one as much. I'd like something here. It tells me the wavelength and frequency of light as well. Here we go. This is half these. So this is the electromagnetic spectrum. We can actually only see a very small portion. We can see the visible range, which is here. It's a very, very small range of the electromagnetic spectrum. Down at this end, you can all see my cursor, correct? Yes? You can see my cursor?
Yeah, we can.
Yeah, we can see, yeah.
So down this end, the low end, this is the low frequency end, which is also low energy, but it's also long wavelength as well. Now, I want you to see what wavelength is here. Wavelength is the distance between peaks. And you can see at the low energy or the low frequency end, the wavelength is quite long. So radio waves here are quite long. And then you've got the gamma rays at the end. There's very high energy, very high frequency. You'll notice the wavelength is very short. So that's what I'm trying to get at here with this. And the other thing I want you to be able to appreciate is the fact that we can only see the visible range is only a very small area. It's this area right here that we can see. That's it. We cannot see anything else on the spectrum.
Do we have to see it with like a microscope? Not a microscope, but some special instrument, or can we see it with the visible eye?
We can't. That's the point. We can't see it with the visible eye. We have to have some sort of other instrument.
Even within that tiny spot that you were pointing out?
No. Well, that's the thing. That's all we can see. That's all that's visible to our eye. We can only pick that up.
Can you think of any examples of something within that range?
Well, anything you're seeing. So let's say you're looking at something blue, it's absorbing red, and then your eyes pick that up. But the thing is that what we can't see, for example, is like infrared. Right? We can't see infrared. We can't see heat. We can't see heat radiation. That's infrared. We can't see ultraviolet, right? That's the rays that come down from the sun, that are outside the range of visible. The sun looks yellow to us. That's fine. We can see that. What we can't see is the ultraviolet rays that come out, the rays that give us sunburn, for example.
All right, I get it.
Yeah, gamma rays we can't see either. All right, so but those are it's silent killers if you're dealing with radiation, because you have no idea. You have no idea. You can't see them.
Yeah, you have to have a Geiger counter.
Yes, something like that. Something that will pick up the gamma rays. But you can't pick them up with your eyes. I guess that's the only point I'm trying to get at here.
All right. Well, thanks for explaining that.
No, you're welcome. Now, what we're going to focus on is the Bohr orbits. And we'll do the energy here, Bohr orbit energy. No, it's not very good. It's not going to be very helpful. I'm not sure if this is going to be that helpful either. All right, I'm going to draw a diagram instead. Now we'll talk about some quantum mechanics later. But we're all aware of the model that allows us to say, well, we've got all of these electron energy levels, and we've got the nucleus here in the middle. This is actually not a very accurate representation of what's going on. It's a very rough representation, because these levels here represent what we call Bohr orbits. Now this is hydrogen that we're talking about here, so it's just got that one proton and one electron. So this would be n equals 1, this will be n equals 2, this will be n equals 3. And it just represents the different energy levels that the electron that's around hydrogen could possibly be in. Now the n equals 1 is called the ground state. That's the lowest energy state for the electron. But what can happen is we can excite that electron and we can send it to another orbit. Let's say we can send it up to n equals 3 by adding some energy. But the thing is, I can send it only to these specific energy levels. I can't send it to halfway in between. So if I put half, let's say I put a certain amount of energy here to get it to n equals 2. If I put in half the energy, it wouldn't go halfway. It would just stay where it was. We call that quantized energy. Because you need a specific quantity of energy in order to get up to the next level. You can't go halfway, is the point. It kind of looks like steps like this. So if you only go halfway, it stays at that level. But if you put in the whole energy, then you'll be able to move up to the next step. This is different to the other possible way it could have been, which is continuous, which is more like a ramp. But that's not the way quantum mechanics works. Quantum. It's because we need quantized energy. We need certain quantities of energy to jump from one energy to the next. We can't go halfway in between. So that's what's going on. Do you have a question, David? Mm-hmm.
Yeah. So if it's going to jump from one energy level to another, you said you need a certain amount of energy, but I thought that if it were to jump from one to the other, it would need more electrons, right?
Well, no, I mean, we've only got one, we're only dealing with one electron here, David. It's because this is hydrogen. We're looking at one electron and we're seeing what happens if we excite it.
Okay. I'm just used to thinking that I'm thinking about like valence electrons, you know?
Yeah, well, yeah, I mean, there's only one electron to deal with here. This is why we deal with hydrogen, because it's the simplest case.
Right. All right.
But it's a quantized situation. Steps, not a ramp, is kind of what I'm getting at here. Now, what's going to happen is that, let's say we send it out to, oops. Let's say we send it out to n equals 4 from n equals 1. So we've put enough energy in to get it out to the 4th energy level. Now, it requires energy, of course, to go from the ground state out to a higher energy level. And then what happens is that the electron can actually fall back to the other energy levels. It can fall back by 1, it could fall back by 2, so it can go from n equals 4 to n equals 2. And when it does that, it releases energy, and it does that by releasing a photon. And that photon is going to be a certain frequency of light. And that photon is also going to have a wavelength, a frequency, and an energy. And we can calculate all 3 of those based upon where it's coming from and where it's going to. But it's always going to go from one energy level down to another energy level. And that's what we're going to be looking at here. We're looking at the energy difference that's going to be caused by the electron falling from one orbit back towards the ground state. As I said, it can be any combination. We can go back by 1, we can go back by 2, back by 3, whatever you want. And that's what we're going to look at. So let's see how we link that to certain formulas. So here's the question that you're going to see, or it's going to be a combination of these kinds of questions. what's the energy, wavelength, and frequency of the line in the spectrum of hydrogen? Let me show you that. See if we can see what it looks like. There we go. See, what happens is, if let's say we're looking for all of these different possible ways that we can get all of these different photons, this is n equals 2. So we're looking for anything falling back to n equals 2. And this would be from n equals 5 to n equals 2. We get this purple line. That would be this line right here. We've got n equals 4 going to n equals 2. That produces the blue line. And n equals 3 going to n equals 2. That produces a red line here. So this is called the emission spectrum of hydrogen. And we can actually see these lines here, or certainly when they're in the visible range, we can see them. And we can then measure the amount of difference in energy between the energy levels by looking at those lines. So that's what this is. That's what this is showing. So let's go back to the question. What is the energy, wavelength, and frequency of the line of a spectrum of hydrogen that represents movement of electron from a Bohr orbit of n equals 6 to n equals 4? So in order to do that, we need an equation, and this is called the Ryberg equation, and you are actually going to definitely be given this. You don't have to memorize this. So we're going from n equals 6 to n equals 4. And that's going to give us an energy. It's going to give us an energy difference. This 2.179 times 10 to the negative 18 joules is a constant. And again, you don't have to memorize that. And the formula is 1 over n1 squared minus 1 over n2 squared multiplied by that. Now the n values are the ones that were given in the question 4 and 6. The thing is, though, that we want a positive value for E. So we want to try and arrange it so that the value we get for 1 over n1 minus 1 over n1 squared minus 1 over n2 squared comes out to be a positive value, which means we have to be choosing what's n1 and what's n2. Now, if we choose incorrectly, what happens is we'll come out with the same value for energy, just with a negative. Now, it's okay if that's the case. That indicates that energy was lost, and that's fine. It's just that then we can't carry that negative value through to figure out the frequency and the wavelength, which are going to definitely be positive values. So what I like to do in this case, I'm going to do 2.179 times 10 to the negative 18. And if I use the smaller n value here as n1, so it'll be 1 over 4 squared minus 1 over 36, or 1 over 6 squared, I definitely know that I'll end up with a positive value for E. Because if I switch that around, I'm going to get a negative value. So it's all plug and chug here. I need it in kilojoules because that's what the question's asking for. So I do a conversion here from joules to kilojoules. So 1 kilojoule over 1,000 joules. And that gives us the energy here, which is a fairly small value, 7.566 times 10 to the negative 23 kilojoules. Does anybody have any questions about where I'm getting any of those values from?
Yeah, I just have a quick question. Where'd you get N1 and N2?
From the problem, you got the Bohr orbits here, n equals 6 and n equals 4. Now remember, it's squared and squared, so that's why I've done 4 squared and 6 squared.
Yeah, all right. So all I have to do is plug it all in,
Yeah.
basically.
Yeah, well, you're given the equation, David. You don't have to memorize it.
Right.
But what I'm saying, the only thing you have to be a little bit careful of, you want a positive value of E at the end. So just arrange the N1 and N2 so you end up with a positive value.
It looks
See-
like currently your N1 and N2 would make it negative because 4 squared is smaller than 6
Yeah.
squared.
But
So
it's 1 over 4 squared. So 1 over 16 is bigger than 1 over 36.
oh, true.
Do you see what I'm saying?
Yeah, I see what you're saying. Okay.
So if you make N1 the smaller of the two, you'll end up with a positive value. That's the bottom line.
All right.
I mean, that's a rule you can take to the bank. That's always the way it'll be.
Okay.
So once we've got that, then we're in a position to be able to calculate the frequency. And for that, we use this formula, which I don't think I give you. I think you're going to have to know this formula. I don't know, actually, maybe I don't know. I'll have to look. I'll look at the test and we'll see. E equals h nu. Now, nu here is the frequency. That's a Greek letter, frequency. Nu, it looks like a V, as you can see there in the diagram. So nu is equal to E over h. Now, what's h? H is called Planck's constant. And Planck's constant is 6.626 times 10 to the negative 34 joules seconds. This allows us to interconvert between energy and frequency. So the energy is going to be 6.566 times 10 to the negative 20 joules. How do I know I need joules? Because I'm given H as being joule seconds. To the negative 34 joule seconds. So I know that these have to match. So joules have to match here. You'll notice that I came up with kilojoules here, but that's 10 to the negative 23 kilojoules. If I didn't convert to kilojoules by dividing by 1,000, I would have ended up with 7.566 times 10 to the negative 20 joules, but those have to match. And that comes out to 1.142. Now, I want everybody to try this in their calculator, please. 1.142 times 10 to the 14 hertz, or if you wanted to, seconds to the minus 1, slash seconds or seconds to the minus 1. All of those are the same thing. So hertz per second, second to the minus 1, cycles per second is the other way of looking at it too. So it's the number of waves that go past a certain point in a second. But I'd like you to try this in your calculator, please. Make sure you're getting the same answer as me.
So for like the hertz and like the seconds to the negative 1, is there a specific one that we have to use for the test, or can we use any of them and the test will mark it as like the
I think it'll
correct
be
answer?
fine. I think it'll, whatever you mark, whatever you put in should be fine, I think. It may even ask for a certain unit, Chloe. I think it does, actually.
Okay, yeah, because I know like the test and like the inserting, like it can be a tricky beast sometimes. So I was just making sure.
Oh, actually,
like,
up here, do you
any
see,
of them I could put it in.
do you see what I said in frequency in hertz? So you'd want to put in hertz.
Oh yeah, okay.
So whatever it says,
Oh, okay, then yeah. So then it'll just be like.
yeah, you'll know. So you can just put in that unit.
Okay, thank you.
All right. Anybody have any issues with getting that number for the frequency of the line?
No, but I
I
did
was
have
just
a
about.
oh, go ahead.
Sorry.
Sorry. I was just about to say that I got the same answer as what you got on my calculator.
Oh, that's good. That's good. Well, that's what I'm looking for. But it's often people will get something like 10 to the negative, or sorry, 10 to the negative 54 or something like that, because they haven't put it in their calculator properly. Roland, do you have a question?
Yes, I just had a quick question about, so like the whole thing with the calculator. So you said that you want us to try it on the calculator, make sure we get the right answer. So are we allowed to use our personal calculator on the
No,
test?
no, no. That's why I'm saying you have to practice with the on-or-lock calculator. But you know, it's a start at least to be doing it, able to do it on your calculator, so you can do it on the on-or-lock calculator too. If you're not getting the right answer on your calculator, it's doubtful you get the right answer on your on-or-lock calculator.
Okay, I just want to sort of clear that up because it made see. Okay, gotcha. Thank you.
But you can practice with the on-or-lock calculator because I give you the link to it in the practice test.
Yeah, I saw that. Yeah.
Yeah.
Yeah. Thank you for that.
All right. Any other questions? Okay.
So
Yeah.
for
Sorry,
this,
David.
How does the equation get affected by what are, I don't know, I'm just a little bit confused with how you get all those numbers. Do those remain constant, E and H, for every single time you do this, or
No,
do they
no,
give
no.
you a different set of numbers each time?
The H is Planck's constant. That's a constant value. The E is always going to be the result of the movement between n values here. And it's the n values that can change, David. It could be, this is 6 to 4, but it could be 6 to 3. It could be 7 to 4. It could be 11 to 10. It could be 11 to 1. It could be anything. But the E will be determined by that difference in n values.
So we got E by doing that equation
Yes,
earlier.
that's right.
That was the product. Okay, that's
Yeah.
why I was confused, because I couldn't
Yeah.
see that you had erased it. But all right, that makes sense.
Well, I sort of erased it, but it's here in the slides.
Right.
Okay. Now you'll notice that it's kilojoules here, but we need joules because our Planck's constant is in joule seconds. So joules have to match, which is why I took the value in joules, not kilojoules. That's important. And the way I get the joule value is just simply not to do this conversion at the end, not to divide by 1,000. So that gives us the frequency. And then we can talk about how to get the wavelength. And the wavelength is going to be from this equation. Oops. It's going to be from this equation. Nu, which we got from the previous problem, equals C lambda. And lambda is the wavelength. Lambda is going to be in meters initially. So lambda is going to equal C over nu. Now what's C? C is the speed of light. That's a constant value too, 2.998 times 10 to the 8th meters per second. And we had our frequency here, which was 1.142 times 10 to the 14th hertz, which is the same as seconds to the -1 anyway. So I'll go ahead and put it as seconds to the -1 to match here. But hertz is the same thing. And it's going to cancel. We're going to end up with meters there. Now, what it's asking for, though, is wavelength in nanometers. So we can do one other step here to convert it into nanometers. And 1 nanometer is 10 to the -9th meters. And if we do that, we'll end up with 2625 nanometers. The reason we would want to do that is now we end up with a value that's a lot more usable, you know, something in the hundreds or thousands. It makes a whole lot more sense to look at than something in the 10 to the negatives or 10 to the positives or whatever. But that's our final wavelength there is going to be 2625 nanometers. You'll always get a result that's in the hundreds or the thousands. Now that's one you might want to try in your calculator as well. The 10 to the negative 9 especially, when you put that in your calculator, it'll be 1 EE negative 9, not 10 EE negative 9, because it's 1 times 10 to the negative 9. So 1 EE negative 9, make sure you do that. Otherwise you'll end up getting it off by a factor of 10. That's a common mistake I see on entering that. People will put 10 times 10 to the negative 9, which is really 10 to the negative 8, effectively. All right, so what have we done here? Well, we've investigated what's happening with the n values as electrons fall back from one n value to another. We get an energy. From there, we can get a frequency. From there, we can get a wavelength. That's what this whole problem is about here. On the test, it's separated out though. All right, let's take a look at. We'll take a look at the test. If we have time, I'll show you the practice quiz as well. But the key to this will be practicing the problems, not waiting to the last minute, of course. I've already given you that spiel. So. So we're looking at Bohr transitions here. You'll notice that I give you these formulas. You see them here. The E formula, E equals h nu, C equals nu lambda. So all of that's given to you. You don't have to memorize any of that. And I also give you these conversion factors as well. 1 nanometer is 1 times 10 to the negative 9 meters, the speed of light and Planck's constant. So I give those to you in all the problems as well. So you can see how you'd have to get the wavelengths, which is what we just did. You have to go through a number of steps to do it, but you can do that. The energy, now you'll notice the energy is given in zetajoules. Now you might wonder, well, what's a zetajoule? Well, I'll give it to you here. 1 zetajoule is 10 to the negative 1 joules, 10 to the negative 21 joules. Frequency, that's in terahertz, and terahertz is 1 times 10 to the 12th hertz. So again, it's given to you in the problems. You don't have to memorize any of that. Now remember that there are videos for all 3 of these. So I'd recommend that you look at the videos too to get some guidance on how to do those problems on the test. But I go through and explain exactly what I'm looking for in those videos too. Anybody have any questions about the test problems here?
So you have the outline to do all those different conversions for the what would you name it? The problems with the wavelength and the energy
Bohr
frequency.
transitions.
That's all in that slideshow.
Yeah, it's all on what we just did in the PowerPoint, but it's also in the videos for questions 4, 5, and 6 for practice test 3.
Right. Yeah, I just need to look at it again because it's really confusing to me.
Well, I think if you watch those videos, you'll be less confused, and then you practice.
Okay.
Practice it, David. Practice, practice, practice.
Yeah.
That's the thing. Practice, practice, practice. And you'll be okay. And one of the questions that really bothers people, I'm putting this out again, it's all extra credit, okay? So this is all extra credit I'm showing you here. We've got so these are the videos I was talking about. You're looking at questions 4, 5, and 6. You want to really focus on those for what we just did. There's also the videos here that explain it too, David. I would watch that too. The ones that involve waves and particles, energy, frequency, wavelength of light, introduction to Bohr transitions, example of Bohr transition problem. I would watch all of those videos as well, David.
Okay.
Let's see. So Bohr transition practice quiz. So one of the questions, and this is the one that really annoys people, but I want to remind you this is extra credit. And I don't mind making extra credit a little bit hard because it's extra credit. These are the different series, and these n values represent the end points. That's the important thing. They represent the end points of an electron falling from a certain energy level. So that's the energy they fall to. So if you look at, let's see if I can find, this is the first one. Here we go. So this is the one that annoys people the most. A line in the emission spectrum of hydrogen has this wavelength. This line is a member of the Lyman series. That tells you that n equals 1. I think that's the Lyman series. If you look up here, I think it's in the, well, it's not, can't see it anymore, but there's something there that tells you that. And the n equals 1, and you're looking for the other n value. So you would have to do a lot of algebra here to work your way backwards through that problem. That's the only clue I'm going to give you about how to do that. But the Lyman series thing, that's given at the beginning of the problem. All right. So that's it for today. We will do a bit more on Wednesday, obviously, and we'll see where we're at. But for now, practice, practice, practice. Practice, practice. Okay. If anybody wants to hang around and talk to me, they can. If anybody wants to hit the road, they can as well. See you all later.
Have a good weekend.
Bye, thank you.
Thank you.
Thank you.
So just to be clear, Monday next week, we're not having class, right?
Mhm.
I think I missed like somewhat of the first part of class. I sort of jumped in on that.
Okay. I sent an email about it.
Oh, you did too? Okay, good.
Yeah.
I think that's about it. See you on Wednesday.
All right. I'll see you.
Have a good day.
See you later, David. Thomas, you there?